Hello everyone. So in the previous video, we discussed about the structure of the various hydrides that are formed by the group 15 elements. So we looked there into the structure of ammonium molecule, and we tried to solve the structure of the ammonium molecule using the VBT theory. And we found that since the hybridization that is coming out while we solved the VBT theory, it was sp3 hybridized, and therefore the structure showed a tetrahedral geometry. Okay, and since one of the hybrid orbital is occupied by the lone pair, therefore the structure of the compound is basically pyramidal. However, the angle has dropped down from the regular 109 degree to a smaller value of 107 degree, and that was accounted for because of the greater lone pair bond pair repulsion in comparison to the bond pair repulsion, and that is why we saw a reduction in the bond angle. Now, let us move on to see what happens to the bond angle when we talk about the other hydrides of the group 15 elements. So here we have the other hydrides formed by the phosphorus, arsenic, and the antimony. All of them, as you can see, the value is coming out to be approximately close to the 90-degree angle. Now, you might ask me why there is a significant drop in the bond angle of these phosphorus, arsenic, and antimony. So if you ask me the reason, one of the reasons that this particular phenomena of reduced bond angle is happening is because as you move down the group of the group 15, you will find that the MH bond length increases. That you can understand because the electronegativity decreases as you move down the group. Therefore, the MH bond length also correspondingly will increase in length. So when the bond length of the MH bond, that is this hydride, this metal can be phosphorus, arsenic, or antimony, when this bond length keep increasing, what happens? The bond pair electrons become more diffused because they are moving away from the central atom. So when this happens, the bond pair repulsions is significantly reduced because now the bond pairs are very far away from the central atom and they are not enough close to show a significant bond pair repulsion. So what happens? The bond pair repulsions significantly reduces. And that's why what happens? It is overtaken by the lone pair bond pair repulsion. So in ammonia, the lone pair bond pair repulsion was somehow withstood by the bond pair repulsion that were present in the case of ammonia. However, the bond pair repulsion was greatly reduced when it starts from phosphorus, arsenic, and antimony. The reason being the bond pair is now more diffused and more far away from the central atom. As a result, what happens? A significant reduction in the bond angle happens, and you get the bond angle somewhere close to the angle of 90 degree. Now, if you see this angle 90 degree, it is the angle that would be the angle for a pure p orbital. Okay, so from this we come to a conclusion that as we move down the group, what is happening is the p character of these bond pair is getting more prominent. The p character of these bond pair is getting more prominent. As a result, what will happen? The character of this lone pair of electrons become more of S character. Okay, so that is what is written down here. The bond pair is becoming more with p character because of the decreased bond angle, and correspondingly the other orbital which contain the lone pair is becoming more of S character. Okay, so this is what is happening in the structure, the pyramidal shape of all the hydrides that are formed by the group 15 elements. There is a significant distortion in the structure because of the prominent lone pair bond pair repulsion, because the bond pair repulsion has significantly reduced on account of increased bond length and therefore the diffused bond pair of electrons. Okay. Now, how does this particular thing affect the Lewis basic character of the group 15 elements? So, Lewis base character is the one that is causing the donor property of the uh, group 15 elements. So ammonia, as we know, it has a pyramidal structure and it contains a lone pair of electrons. So that pair of electrons, since they are available for bonding, they act as Lewis bases. And because of their Lewis base character, they act as a Lewis base as well as they can act as a ligand to form various coordination complexes. So both these acting as a Lewis base or the feasibility as a ligand for a formation of coordination compounds, both are possible as a result of the Lewis basicity of the ammonia molecule. So that thing significantly reduces as we move down the group, and that we can easily understand from the thing that we discussed just now, that lone pair is now having more of a S character. As a result, what happens now? S character is having a spherical geometry. Now, S character, since it has a spherical geometry, the directional property of the lone pair is completely lost. And therefore, they are more diffused now, and therefore diffused lone pairs are not very good at being a Lewis base, okay, or as a donor. So that is what is happening. So in the case of ammonia, okay, so in the case of ammonia, if we talk about just ammonia molecule, it contains the lone pair and they are pretty much available for acting as a donor. However, when it comes to the other hydrides like phosphine, the lone pair is now occupied in the S orbital. Okay, they are more spherical geometry, they loses their directional property and therefore they are more diffuse. As a result, what happens? The lone pair electron is kind of now spread over the central atom, that is phosphorus, and they are not so much available for donation, and therefore this considerably reduces the donor property of the phosphorus in comparison to ammonia. But still what you find is that in the case of the phosphorus, they still form, still act as Lewis bases, and they also have complexes in which they act as ligands. Now, why this is possible? We just now said that because of the S character of the lone pair, the Lewis basicity or the donor property of the phosphorus lone pair is considerably affected. However, here we see that they are acting as a Lewis base as well as they are acting as ligands in these complexes. Now, what is causing these things to be stable? Now, that thing is because of the back bonding that is possible in the case of phosphorus. Because we know phosphorus contains empty 3D orbitals. So what happens? When it forms a coordinate bond with the metal, the filled d orbital on the metal can back bond with the empty 3D orbital on the phosphorus. As a result of this back bonding, that sideways overlap between the filled d orbital of the metal and the empty d orbital of the phosphorus, we get a d pi back bonding. And this back bonding, that is d pi back bonding between the filled metal d orbital as well as empty p d orbital, we get the stability to form these kinds of Lewis bases as well as these kind of complexes. Okay, so that is why in case of phosphorus you find an increased these formation of Lewis spaces or acting as a ligand in these complexes. So this particular thing is completely lost when we talk about the hydrides formed by arsenic as well as antimony. And that is because if we come from phosphorus to arsenic and antimony, what we find is that the d orbitals is becoming more diffuse, because in arsenic it is 4d, in antimony it is 5d. They are much larger and therefore more diffuse. So because of that, the back bonding strength is considerably reduced when it comes to arsenic and antimony. So the stabilizing factor that is available in the case of phosphorus because of back bonding is not so much available in the case of arsenic and antimony. And that is why, even though they little bit able to coordinate using the s electron, they are not significantly balanced by the back bonding. As a result, their donor property is significantly reduced. Okay, so this is the reason why, as you move down the group in the group 15, the hydrides loses its donor property, and therefore acting as a ligand or acting as a Lewis property greatly reduces as we move down the group in the case of group 15 elements. So I hope you are pretty now clear with the things that we discussed just now regarding the hydrides. In the next video, we will be talking about the oxy acids of nitrogen and discuss about their structure and probably about their acid strength. Thank you very much for your attention.